Welcome to course 12.340X, Global Warming Science. I'm Kerry Emanuel. Together with my fellow instructors Dan Sitsko and David McGee, I'll be taking you through this course of instruction on one of the most interesting problems in the natural sciences. We'd like to begin by thanking Heidi Cullen and Sherry Bell of Climate Central for providing introductions to the course. Let's begin by talking about the purpose of this course. We'd like each student to come away having developed an appreciation and a broad understanding of the Earth's climate system, to understand and use some of the basic tools of climate science, and to develop an awareness of possible consequences of climate change. We should also talk about what this course is not. In particular, this is not a course about the politics or policies surrounding the issue of global warming. These are important subjects, but they won't be covered in this course. You might be wondering what you should have under your belt to take the course. First of all, it's necessary to have a background in calculus through ordinary differential equations. It's helpful if you have a background in partial differential equations as well, but this is not necessary. You should have had basic physics courses in mechanics and electromagnetism, and it will be helpful if you've been exposed to the science of thermodynamics. Let's begin with a broad brush overview of what we intend to cover in this course. The world is warming. Let's look at the evidence for this. The graph in the lower left shows a reconstruction of the global mean annual mean temperature as analyzed by two different organizations, the Hadley Center in Britain and the Goddard Institute for Space Studies in New York. Both analyses show that beginning at the end of the 19th century or early 20th century, the Earth's mean temperature has risen about 0.8 of a degree centigrade. The graph at the top shows the global pattern of this warming. This is a graph showing the tendency of the mean temperature change between the 1950s and the first decade of the 21st century. What we can see in this graph is that most of the warming is over continents and in the northern hemisphere. Why is the world warming, and why is it warming up with this pattern? What can science say about these two graphs? We're going to address several questions that are central to the problem of global warming. First of all, what do we mean when we say climate? What exactly is climate? What physical, chemical, and biological processes control climate? How has Earth's climate varied since the formation of the planet, and why? How has climate been varying on the timescale of human history, and why? What tools are used to study climate, and how might climate change in the future? Let's begin with the definition of climate. Now we can think about some popular definitions. A lot of people will tell you if you ask them that climate is just the average weather. Or climate is what you expect, but weather is what you get. But in our profession, the technical usage is a little bit more sophisticated. We think of climate really as the statistics of weather. And these statistics include not just the average weather, but the statistics of its variability. And these statistics are commonly calculated over periods of 1 year or more. So the seasonal cycle, the progression of the seasons, is not considered an example of climate variability. So through this course, we're going to stick with the professional definition of climate simply as the statistics of weather. Here are some examples of climate variability you might or might not be familiar with. One example is El Niño, La Niña cycles. El Niño is a dramatic warming of the central and eastern equatorial Pacific. It occurs not periodically, but with an average interval of about 2 to 4 years. And when it happens, it changes the weather quite dramatically all around the tropical Pacific and as far away as North America and even Europe. Knowing how El Niño works lends a little bit of predictability to the climate. Another example of climate variability is the Little Ice Age about 100 years ago. We're not quite sure whether this was a local phenomenon that just affected the North Atlantic region or whether it was truly global, but it was associated with quite cold weather through Central Europe. This is a period when the Dutch landscape paintings of the 17th century showed lots of Dutch people skating on their canals, which was common then but rarely happens today. Another example of climate variability, which is much more cyclic in nature, are the great glacial interglacial cycles, which have been going on for about 3 million years and which have periodicities ranging from 20,000 to 100,000 years. A very interesting climate phenomenon is the Paleocene-Eocene thermal maximum, a spike in global temperatures that occurred about 50 million years ago. From what we understand from paleo records, this took about 20,000 years to develop and about 100,000 years to go away. An even longer example of climate change is the gradual cooling of the Earth from its maximum temperature in the late Cretaceous to about the present, spanning a period of about 15 million years. So climate variability can occur on timescales of a few years to basically the history of the Earth.